This conference will now be recorded.
Very good evening, students. Today we'll be concluding this chapter electrostatics by learning few important properties of conductor. These properties are very important in the sense there could be conceptual questions in NEET exam or some other exams, IIT, JEE, etc. So we should learn these properties of conductor under static conditions very carefully. Okay, so let us learn one by one. See, you know this conductor, such as metals, they possess free electrons, right? So conductors generally have free electrons. Okay. And if there is a potential difference or electric field inside this, then these charges will be experiencing forces, and that's how they will be accelerated. In this sense, not accelerated, they will have drift motion. Okay, upon applying electric field, they will have drift motion or constant motion inside the conductor, and thus there will be flow of current. Okay, but what happens at the static condition? At the static condition, that means when electrons or charges are not moving. Static condition means, so static condition means charges are not moving. Okay, or here I can say directly electrons are not moving. So electrons are not moving, okay, in the static condition. So if electrons are not moving in the static condition, then what is the implications we get from here? See, if resultant electric field exists inside the conductor, these electrons will actually experience a force and they will move, and that's how we get current, okay, as the electrons move. So what is happening? There should be some resultant electric field inside that conductor, then only there will be flow of charges. Okay, flow of charges, and there will be current. But if the electrons are not moving, what does that imply? That implies that no resultant electric field will be there inside, or electric field will be zero inside a conductor. Inside a conductor under static condition. This is important. Okay, under static condition. Okay, so these are few very general aspects, and based on these aspects we'll be learning, or we can be able to prove few more important properties which are really interesting to learn. So what are those? First of all, the first property of conductor is that this, you should remember, this is under static condition. Excess charge on a conductor resides on its outer surface. What does this mean? Suppose I have a conductor like this, in any arbitrary set. If I put an isolated charge, suppose positive charge, okay, some isolated charge inside the conductor, then what will happen? The whole charge will come onto the surface. Whole charge will come onto the surface, and that charge will be actually uniformly distributed over the surface. So as a result, what will be there? inside there will be no charge. There will be no charge. So excess charge means any free charges. Okay, excess charge. See, inside the conductor there will be positive and negative charges, nucleus or the core shell, electrons will be there. That is fine. But the charges which are free from the atoms, their atoms. So excess charge. This word is important. Excess charge will be residing outside the surface of a conductor. But you might be thinking, how do we prove this? Okay, let us suppose uh, this is an arbitrary. I think I have one. Let me check. Yes. So I have taken an arbitrary conductor, arbitrary shaped conductor, and you look, I have given some isolated charge Q here, and that has gone to the surface of the conductor and residing on the surface of the conductor, and distribution of the charge is uniform. So to prove that, let me consider a Gaussian surface inside the conductor. See, inside the conductor, this is the surface. This is the surface of the conductor, or boundary also you can say. So this is my Gaussian surface. As you see, this Gaussian surface is inside the conductor. Now, just few minutes back, what we have learned? We have learned that there will be no, when there is no current flow, then there will be no resultant force or electric field, must be zero inside the conductor under static condition. So if I apply Gauss's law, see, I can write E, suppose arbitrary area S of this Gaussian surface area here, like area of the Gaussian surface is S, and on the right hand side Q enclosed, I can write enclosed ENC divided by epsilon naught. Okay, now inside the conductor electric field is zero. So what does this imply? So this implies that Q enclosed by the Gaussian surface is zero, right? So what does this mean? See, this Gaussian surface has been taken inside the conductor. So this is arbitrary Gaussian surface. I can take anywhere like this. I can take smallest to as good as or as large as up to or before the surface. Okay, before the surface. So I can choose any Gaussian surface inside the conductor and I can get the same result. Q enclosed is zero. So this implies, so thus we can prove. So thus we can prove that this is Gauss's law, applying Gauss's law. Okay, so an excess charge reside outside. Sorry. Excess charge always reside on the outer surface, on the outer surface of the conductor. Okay, so this is one point. So one property that excess charges resides outside the conductor. Now, electric field at any point very close to the charge conductor, very close to the charge conductor. So what does this mean? Also, this is actually sigma by epsilon 0. So this is what it is. So what it is saying, if I have any arbitrary step conductor, just outside that, just outside, at any point outside, just outside any point I take, the electric field will be always sigma by epsilon 0. So this is the one. So electric field at any point close to the charge conductor is sigma by epsilon 0. So how do we prove that? So here, as you see, I have considered this as a conductor, and see, I have Gaussian pillbox as a Gaussian surface, Gaussian pillbox as Gaussian surface. Okay. And in this case, see the Gaussian surface. So this cylindrical, or I can say pillbox. This pillbox is actually having cylindrical shape. Part of, see, one surface or one part of, or half, I can say half of the pillbox is inside the conductor, and outside, just outside, it is actually just for representation. This has been taken such a long, otherwise just like this, just on the surface, just outside the surface and inside the surface, it is very close to the, so these flat surfaces are very close to the boundary of the surface. Okay, so I have taken arbitrary shape, and I have taken this Gaussian pillbox having cylindrical shape, and this area, suppose this area of cross section of the flat portion is delta S. So this side also it will be delta S. So if I apply Gauss's law here, apply Gauss's law, if I apply Gauss's law here, what you see, I have three surfaces to calculate the flask, right? So this is inner surface, you can see that. So if I write flask inner surface, inner, then I have flask through outer surface, outer, plus flask through curved surface. Okay, curved surface, and that will be is equal to charge enclosed by epsilon 0. So this is the Gauss's law, right? Now in this case, you look, by symmetry the electric field always radial. Okay, so for curved surface the electric field will be tangential, isn't it? So electric field, so this I can say 0 because E is tangential or parallel, tangential to the curved surface. So there is no way to have flux through it, electric flux through it. What about inner one? This is 0 because inside electric field is 0, as electric field is 0. So only thing is this one. So this, see here, the surface area is delta S and E is the electric field, so I can get the flux, isn't it? For this one, see E into excuse me, E into delta S, and this is Q by epsilon 0, right? So I can write E is equal to Q by delta S into 1 by epsilon 0, and see Q by delta S, this could be written Q by charge by area. So this is surface charge density sigma divided by epsilon 0. So you can see that electric field at any point very close to the charged conductor excuse me, very close to the charged conductor will be E is equal to sigma by epsilon 0. So this is proved. Now here I have two corollaries. Electric field changes discontinuously at the surface of a conductor. Just inside the conductor it is 0 and outside the conductor it is sigma by epsilon 0. We have seen that. So electric field is here 0 and just outside it is. So inside anywhere you take it is 0 only. So here also it is 0. Suppose I have A point and outside, just outside it is B point. So electric field at A point is 0, whereas electric field at B point just outside the surface it is sigma by epsilon 0. That means there is a discontinuity. Okay, there is a discontinuity. So electric field changes discontinuously across the surface of a conductor. Okay, and now one more point is that the electric field over the conductor surface will be different actually over the conducting surface. See, suppose I have such a conductor and you see here the curvature of this surface, this point, suppose this is the point, so here curvature is more than here, isn't it? And you know the surface charge density is inversely proportional to the radius of curvature. Radius of curvature. That means over the surface of a conductor, the surface charge density depends on the curvature at the respective portions. Okay, for this portion 1 here, see here, if I say sigma 1 is the surface charge density, and at this place, if this sigma 2 is the surface charge density, as I said, according to this, excuse me. As the radius of curvature is less here, so sigma 1 will be greater than sigma 2. I hope you agree with me. Because radius of curvature here is more than, see, if I write radius of curvature here R2 and here R1, actually R2 is greater than R1. Radius of curvature. So that's why this follows this. And since electric field is sigma by epsilon 0, that means electric field is also directly proportional to the charge density. So this implies again electric field at region 1 is greater than electric field at the region 2. So this is how over the surface of a conductor the electric field can vary. It cannot be a constant. It depends on the radius of curvature of that particular portion. All right. Now another property is that the electric field and field lines are normal to the surface of the conductor. Normal to the surface of the conductor. So as you see here, at each portion the field lines, see field lines inside there is no field line because there is no charge. So field lines will be starting from the surface and it is going out on the surface perpendicular to the surface actually. At each point you look, this is the tangent towards the tangent to the curve here, and this is 90 degree. Okay, so thus at each point electric field or electric field lines to the surface of the conductor, it will be normal. Okay, it will be normal or perpendicular. Now very interesting and important thing we are going to discuss, that is the cavity inside a conductor. Cavity means just a hole inside the conductor. If there is a cavity inside the conductor, then if I keep a charge over here, see, if I plus Q inside the cavity, then what will be the electric field inside the cavity? Inside the cavity. See, we can apply Gauss's law to find out what will be the electric field inside the cavity. See, inside a cavity, see if this is the Gaussian surface, this is the Gaussian surface. What happened? Inside the cavity, actually electric field will be zero. See, electric field will be zero inside the cavity. Okay, inside the cavity. Electric field is inside zero inside the cavity. How do you analyze that? Actually, to analyze, we can do two things. One is that, see, if I keep a positive charge Q, this, see, it is conductor, right? This is conductor. Suppose neutral conductor. Conductor. So if it is neutral conductor initially, if you put a charge now, what happens? See the near surface of the cavity. See, this positive charge will actually uniformly induce says negative charges, negative Q charge. So this positive Q charge will induce, see, induces equal and opposite negative charges distributed uniformly inside or inner surface, at the inner surface of the cavity. Okay, inner surface of cavity. All right, so if this is the case, see, as a whole, when we take a Gaussian surface just outside the cavity, look, this is the Gaussian surface. Now if we apply Gauss's law, so E into S, suppose the area of the cavity, or Gaussian surface, sorry, area of the Gaussian surface. Now this side it will be Q enclosed by epsilon 0, right? So what about this value? Since I have equal and opposite charges inside the Gaussian surface, so Q enclosed will be 0. So if this Q enclosed is 0, then what it implies is electric field is also 0 inside the cavity. So inside the cavity, electric field is 0. So that is what we have proved here. Now, see, one more point I would like to say. See, then how come this positive charge comes outside? If this is neutral in nature, you know, when the inner surface of this cavity is induced by negative charges, these negative charges will induce positive charge outside the surface of the cavity, outside the cavity. Okay, outside the cavity. I hope you have understood this. Suppose that this was initially neutral, this cavity, inside this cavity, if I give a positive charge, then it will induce equal and opposite negative charge just on the inner surface of the cavity. Then that charge will induce in turn positive charges outside the cavity. Okay, outside the cavity, in the sense on the surface of the conductor. Okay, so that's how we get these positive charges. Otherwise, it is neutral. Okay, otherwise it is neutral. So due to this induction, we get positive charges. Now, yes, now we'll see here in the figure B. Look, since since here positive and negative charges are there will be electric field lines like this, as you see. They will end inside the cavity itself. They will not penetrate. They will not penetrate to come out of the surface. Okay, so come out of the cavity. They will not. So this electric field lines will not penetrate the conductor. Okay, so they will be just confined inside that. These field lines will be confined inside the cavity, as there are negative charges here. Positive, see, field lines will start from positive charge and ends at negative charges. So, but the originally you will get the electric field due to the surface charges. Okay, due to the surface charges. Actually, these electric field lines are not penetrating as they are, like as you see outside. These are actually due to the charges on the outside surface. In fact, inside the cavity, net charge also will be 0. Now, electrostatic shielding. See, we can make use of this cavity concept. We can make use of cavity concept. See, suppose if I keep, see, if I keep this positive charge inside the cavity, and then we bring anything, any source, electric source, which has very large electric field, etc. If I bring that near to this cavity, will that make very large difference? No, because it cannot affect the electric field inside, because see, inside the cavity it is not going to penetrate to the like cavity, or I would say there will be no interaction between the cavity and the electric field or sources of electricity, or sorry, sources of charges, etc. outside the cavity. So that's why it is called shielding. That's why it is called shielding. If you keep anything inside this cavity, then the external electric field or charges will not be able to affect in any way this charge inside the cavity. So very sensitive electronic instruments are actually kept inside such cavity, which are called electrostatic shielding, which are called electrostatic shielding. Okay, so if you keep any sensitive instrument inside the cavity of like inside the conductor, say conducting box, in see sometime the wrappers we get for electronic instruments will have the aluminum coating or some metal coating, copper coating, because we just want to keep the instrument, okay, the instrument inside very safe, or very much sensitive instrument can be kept inside the conducting box or inside this kind of conducting cavity. Then external fields or external electricity cannot affect this one, okay, this instrument, and hence it will actually be very sensitive, very sensitive. It can give very precise measurements. Okay, so electrical shielding or electrostatic shielding we have learned already. Now we'll see potential of a charged conductor. Potential of a charged conductor throughout its volume is same. What does this mean? What does this mean? Suppose I have a conductor. Sorry. I have a conductor. See, if I give a positive charge here, all the charge will come on the surface, isn't it? And it will be distributed uniformly over the surface, right? Yes. So then what happens? See, in fact, inside the cavity, see, inside the conductor, there will be no charges, only charge, or I can say in other words, there will be no electric field inside the conductor. Okay, under the static condition, electric field will be zero inside the conductor. We know electric field is minus dV dr or dV dx. Okay, dV dx. Now, now this left side is zero. That means you know dV dx is dV dx is zero means V is constant, isn't it? Some constant. So inside everywhere electric field is zero and potential will be constant throughout. Okay. And see, in such case, if suppose there is a spherical this kind of conductor, spherical conductor, then what will be the electric field, potential just on the surface of the conductor. So that will be actually given by Qy 4 pi epsilon naught R. Okay, so R is the radius of the conductor. Okay. So everywhere we can see electric field is zero as well as this is constant. If this is constant, this is called actually equipotential surface. This is called equipotential surface. Equipotential surface. So equipotential surface inside, that means everywhere the potential is the same. Electrostatic potential is same. I should not say zero. Now, if it is same everywhere, all right. So this is called equipotential surface. Now we'll move on to some other topic, that is electric field and potential due to a charged spherical cell or solid conducting sphere. Okay, solid conducting sphere will just take up later. First we will take electric field and let us say potential due to a charged spherical cell. So spherical cell cell means inside it will be actually hollow, just a hollow sphere. Now look, if I have to calculate the electric field, since it is a conductor and you know for conductor inside there will be electric field zero, right? That is for sure, because if this is mine, see I have the conductor of radius capital R and see inside there is no charge at all. The charge is outside. So if I draw any Gaussian surface like this and write the Gauss's law, then it would give zero. So what does this mean? Spherical cell, inside the spherical cell electric field is zero. So this is one point. So electric field inside is zero. Okay, this is inside point. Now what about electric field outside? Now just see, this is the Gaussian surface. Suppose I have a point P where I am calculating electric field due to this spherical cell outside, at any point outside the cell. So this I can say as P. So this P has this Gaussian surface has got radius smaller and the original cell is having radius of curvature capital R. So see, I have into area is equal to charge enclosed by epsilon 0. Now let us see one by one. In this case, you know this by symmetry, electric field will be constant at each point of the Gaussian surfaces. So I can just take out this E out of integration. But what about this S? See, S also, this is a spherical Gaussian surface. I can write down the surface area 4 pi r square, 4 pi small r square, and this is Q enclosed. So Q enclosed is Q. I'm just taking. So Q enclosed is Q divided by epsilon 0. Now what is this? Q by 4 pi epsilon 0 r square. See, at any point outside the cell is having electric field variation as 1 by r square, just like a point charge is sitting at the center of this cell. That means, you know, when you consider any outer point to calculate the electric field at so electric field varies as 1 by r square outer point at any outer point. Okay, for outer point, we can consider the whole charge to be concentrated at the center of the spherical cell, just like treating as a point charge. Okay, it is treating as a point charge. But it will be very interesting when we'll go for solid sphere. So if I see, I have got then two results. See, I'll write here. One result is E is equal to 0 at any inside point, and E is equal to E is equal to Q by 4 pi epsilon naught r square. This is actually, this point is greater than the radius of the Gaussian, of the spherical cell. Now I have got two limits. What about electric field at the just surface? Surface will get Q by 4 pi epsilon naught capital R. So this is capital R square just on the surface. So you look, if I draw the electric field, see on the surface it is Q by 4 pi epsilon naught r square, as I said. So this is the surface, and inside that it is 0. So this is actually electric field 0 at this position. Okay, see up to the radius, that means after surface there will be a variation 1 by r square. So this is this. So this is up to here, it is r, and this point is r greater than r. Okay, so electric field is varying as 1 by r square outside, and inside it is varying, it doesn't vary, it is 0. So this is for a spherical cell. Spherical cell means there is no spherical cell means there is no electric field inside, there is no electric charge inside. Okay, all right, so this is the thing. Now we'll move on to the potential part. See, in this case, potential part is very easy. Look, we have already found out potential is Q by 4 pi epsilon naught r for any arbitrary point outside. This is outside. What about inside? It is actually Q by 4 pi epsilon naught capital R. That is actually inside. Inside potential is this. Now, how do you get this potential? We can just go for electric field. See, for electric field outside point, we have got q by 4 pi epsilon naught r square. See, so from here, can we find out potential from this electric field? Answer is yes. So we know dV here with the minus sign. With the minus sign, minus dV here is equal to the electric field q by 4 pi epsilon naught r square. I can write here. Okay. Now, if you integrate it to get, see, this is V at infinity, and this is let us say this V is 0 to V only. So q by 4 pi epsilon naught r square into dr. Okay. Now, if we integrate this, you know what we get? We get q by, and here it is actually r is equal to infinity to r, say. So this is anyway V outside, and if we do the integration part, then what you get? Potential. So q by 4 pi epsilon naught r actually. With the minus sign, minus minus gets cancelled. So this is q by 4 pi epsilon naught r. Okay. And inside, see, at the surface, see, surface, just r is equal to r. That is surface value. Capital R. So till surface, from starting from center till surface, the electric field. See, we have seen here electric field. Now we'll see electric potential. So this is actually q by 4 pi epsilon naught r. So this is the surface potential. This is having some value. And the outside point, see, outer side, that means it is outside the okay. So this is outside the surface. Okay, this side. So you can see that variation of the electric field. Okay, so this part is constant. You can see this part is constant. This is actually going inversely. Okay. All right, we'll go to the next. Electric field and potential due to a solid sphere. This is much more important. I think I'll stop it here for today. Tomorrow I'll just take, because it will take a little more time. So tomorrow I'll take up this topic, this single topic, and take up various numerical problems and conclude it. I think, yeah. So we'll stop it here for today. Thank you for your patience. Bye for today.